Good morning and welcome to Advent of Code in F#. We're at day 8 already. Before we dive into today's puzzle, I want to quickly come back to the day 7 solution we made. Because there was one thing I was not happy with, and that was the pattern matching I was doing. So remember from yesterday we were applying rules of bags containing other kinds of bags, and there was this part where I was pattern matching. I was using pattern matching, and if it was an empty list I would do nothing, and if it was a non-empty list I would do something. Well, it turns out that you can always do the non-empty list case and it works out just fine. So breaking this up in a pattern match was not necessary, and I didn't do that just once, I did that twice. So both those pattern matches can go, and the code cleans up a bit after that. So parsing is still terrible and I still suck at regular expressions, but the recursive functions to find which bags can, or how many bags the shiny gold can contain, that cleans up nicely. Anywho, let's look at day 8. Handheld halting. Halting problem? That would be interesting. Our flight to the major airline hub reaches cruising altitude without incident. While we considered checking the in-flight menu for one of those drinks that come with a little umbrella, we're interrupted by the kid sitting next to us. Their handheld game console, of course it's a Nintendo Switch, won't turn on. They ask if you can take a look. So yeah, there's an infinite loop. We are talking about the actual halting problem from Turing. Is it Turing? Don't remember. In the boot code, your puzzle input of the device. So we have boot code and it has an infinite loop. And we even should be able to fix it, but first we need to be able to run the code. Oh no. It begins. Puzzles were fine and fun until day 8, but now we are going to write an assembly language interpreter again. Yes, we are. This has happened a couple of years in the past. It's not the first time Eric nudges us towards these kinds of puzzles. The boot code is represented as a text file with one instruction per line of text. Each instruction consists of an op and an argument. Yeah. How many do we have? Oh, we start with 3. Chill. Ac increases or decreases a single global value. So yeah, let's do something to an accumulator. Oh yeah, it's a single global variable called ac for accumulator, and you can alter it by giving it a delta, an increase or a decrease. Starts at 0, cool. And then we advance execution to the next command or the next instruction, yep. Jumps to a new instruction relevant to itself. An offset from the jump instruction. So jump +2 would skip the next instruction. Jump +1 would continue as we would normally, and jump -20 would go 20 lines above. Yep. Nop is nothing. Just some padding. Okay, so example program. Do nothing but move instruction pointer 1 down. Increment the accumulator by 1. What's this doing here? Now there's nothing, accumulator is increased, and jump 4 sets the next instruction to the other ac +1. 1, 2, 3, 4. Yeah, that's correct. After it increases the ac from 1 to 2, jump -4. Yeah, then we go here, and then 1, 2, 3, 4, back to the ac +3. Yeah, makes sense. This is an infinite loop. With this sequence of jumps, the program will run forever. The moment the program try instruction a second time. Okay, so we just need to keep track of which instruction we executed, or which line of code. And whenever we hit the same line of code twice, you know it will never terminate. That is the case for these kinds of programs because we can't do any comparing. We just do plus, minus, jump, and nop. So yeah, they're right. If we visit an instruction twice, this is an infinite loop. And immediately before the program would run an instruction a second time, so immediately before we detect the loop, the value in the accumulator is 5. So okay, we need to keep running the program until we detect, oh, we're going into an infinite loop here. We've already visited this line of code, or this instruction, and then we need to look at the value of the accumulator. Cool. Let's grab our input. How big is our program? Pretty big. Yeah, pretty big. Input. So, I have the luxury of already having seen these kinds of puzzles in previous years, so I kind of know where I'm going right now. I like to solve these instruction or assembly language exercises with a fold again. So we just take the instruction set and we start. Is it a fold actually? No, it's not a fold. Forget I said that. Let's just take a look at the problem. One thing we already have to do is parse the instructions, and there's only 3 kinds of instructions: ACK, jump, nop. Let's represent it with a union type. So what do we have? ACK, and that you get something ACK plus 7 or ACK minus something, ACK of int. So is it not okay to give it a lowercase? No, it's not okay. Okay, we have jump with an offset, and we have nop. Don't do anything. So these are the 3 kinds of instructions. Let's write a parser. Let's first read in our input. What's the string interpolation thing again? This, and then this. I think so. And there's this magical keyword. Come on. This was actually what I was trying to do. This is the variable part. There we go. It always takes a while to what's not right here. Source. There we go. That is indeed my path to my error. Okay, there we go. So these are the instructions. Let's parse them. I tried to show you active patterns yesterday, and I think today might be a better fit for them. Let's see how far we get without, and then let's pattern match on whatever we get in. So the nop is easy. If we get a line that says NOP, hey, interesting. Nop also has a number or an argument. Every instruction has an argument. Yes, every instruction has an argument. I should have read the exercise more attentively. So, yeah, active patterns might actually be an elegant solution to this. Otherwise I have to do some kind of I dot starts with. Let's give it a type. So let's pattern match on what we get. Why does it keep autocorrecting? This should be one way of doing it. Then we need to parse the remainder. There's also another way I've used in the past. We're using the fact that a string is a sequence of cars, a list of cars, and you can pattern match on lists quite easily. So this there's a sequence of numbers in there, so this should also work. And let's parse the arguments to a number. Int arg does not like that. Sekar, maybe if I do this. List of characters. Interesting. Again, I'm doing it, and you can't pattern match on that. That is true. So yeah, this is one way of doing it. It's a bit of a funky way of doing it, but what's that called? The cons operator. You can use that in a pattern match. Does not like this. It does not like this. So parse the int and make it a nop. Oh yeah, and that's oh, that was the problem. Arg is a list of characters, so let's make it a string again, and then make it an int. Okay, so that works on strings, not characters. Okay. All of this just to ease up on the pattern matching. I don't know if I like where this is going actually. Yeah, because then we have to make, okay, so that's actually pretty easy. So it's complaining that it requires a list of characters, but it's a string, and strings are implicitly sequences of characters, I think. So I'm guessing if we do a toList before we parse, it'll work out. Yeah. So this is now able to parse our NOP, but it's quite verbose. Let's do cleanup later. Let's first make sure we're on the right track. So this is NOP, jump and ACK, I think are exactly the same. Jump, J, MP, and that's a ACK, and that's a jump. And anything else we encounter, let's just fail really hard. Oh, it does not like, you can match on with an underscore, like a catch everything. But it doesn't seem to like having that in a string interpolation. Okay. Let's see if we can parse our given input. So this was the easy part, the parsing. We're already 20 minutes in. ACK7, ACK23, ACK41. ACK7, ACK23, ACK41. There's a plus and a minus. I didn't even remember. Is it parsing negative numbers correctly? So 3 ACKs a jump and an ACK minus 17. That's 0, 1, 2, 3, 4. Let's take a look at element number 4. Let's make it a list. Oh, there we go. That was enough to print out the entire instruction set. ACK minus 17. Yep, looks correct. Let's keep forging ahead. So we now have the program. We have a parse our program. Next up, we need to run the program. It's not a fold. It's we could do with non-fold. Yeah, we could do it with non-fold, I think. Or just a recursive function that keeps going. Let's use a recursive function today. But anyhow, we need to keep track of some state, because now we just have a list of instructions. That's not everything we need. We also need an instruction pointer. So I'm going to make something called... It's not actually a program. What is it? Is it a runtime? Is it state? Let's call it state. It's a record type, and we have an instruction pointer, which is an integer or a number. And we have the global variable called accumulator, which is also a number. And that's enough to run our program. But if we need to detect loops, we also need to keep track of which instructions we visited. And maybe there's duplicate instructions in there, so I think we're gonna have to, or my suggestion is to keep track of the list of instruction pointers we've been executing. So this is the instruction pointer for the next instruction, but let's keep a set of visited instructions pointers. That's more clear. And it's an int set. So we keep track of whatever we visited. Initial state, let's make a quick function for it. So instruction pointer starts at the first instruction, I'm guessing. What do we need? Value in the accumulator, so it does not matter whether we use a base 1 or base 0 indexing. Let's go with 0. Accumulator starts at 0 again. I think I read somewhere. Yep. Visited is a nothing. So an empty set. Okay, cool. We're almost there. Let's write a function to just take one step. So a function to run one of the instructions. Run next to run the next instruction. Does that make more sense? It doesn't really matter. So we have instructions, or let's keep them implicitly for now. Sure. No, let's make them explicit. And we give some state. Next instruction is state. No, is the instructions at instruction pointer, and we keep track of that in our state. So this is reading the next instruction from the instructions, and then we need to execute or run the instruction itself. Let's pattern match. What is the easiest case? Nothing. So if we have to do nothing, we just increment the instruction pointer by 1. So that's the original state with instruction pointer is state.instruction pointer plus 1. So just increment by 1. What's not okay with this? It does not know the type of instructions. Okay, so let's give him the type instructions. What's it called? Instruction type? Yeah. There we go. So we increment the instruction pointer, and let's also keep track of which instructions we visited. When do we need to keep track of the instruction we visited? Before we run it or after we run it? Let's go to the example and see how Eric does it over there. So the second we notice, hey, this instruction pointer is in our list of visited, we can fall out of the program. So that means that before we do this, actually we have to check for visited instructions. Let's forget the loop. Let's forget the infinite loop for now. Let's just forge ahead until we have a actual infinite loop. An actual infinite looping program. So, what's the easiest one? Jump? Sure. Jump with an offset. And that's just incrementing the instruction pointer with the offset. And ACK. ACK is actually more akin to doing nothing. ACK is the bumping of the instruction pointer, yes. But also, let's, okay. So we increment the instruction pointer by 1 just to go to the next instruction, but we also adapt the global accumulator with the delta we're provided. So I think this actually runs our program, or that's runs a single instruction for our program. So how do we keep running? It's funny that I actually have to think about how to implement an infinite loop in F#. Just write a recursive function, sure. Yep. So what is the actual program? What does it look like? It's actually using run next. So I'm having a hard time. Okay, there we go. What am I actually trying to do here? I'm not sure. Let next state is, yeah, and then we just run the program, same instruction sets, but the next state. This is our infinite loop, and I can't believe it took me 5 minutes to figure out. I think this is enough to watch it blow up in an infinite loop. So let's try that. Let's try to run it just for fun. With the initial state. Let's go! No! What does this return actually? It's a infinitely looping thing, so it's a unit. So that's basically the void for F#, which is actually saying hello side effects, or in this case hello infinite loops. Yeah, so we're My REPL crashed. I take it that we're in an infinite loop. Let's roll back. And let's think about this infinite loop thing. So we already have a set of visited instruction pointers, and this is the moment we visit the instruction pointer. So let's just let's just update the instruction pointer. Yeah, I'm just gonna do it for every command. We only have 3. Let's not go crazy. And let's add, it takes the value first. So it's this. Add to that set the, it feels weird to do it here actually. Should we use the next instruction pointer or the current instruction pointer? Okay, back to the example. I'm not sure. First, an observer does nothing, blah 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 blah. So when we execute a instruction, jump 3, we jump back to, so that for us that means we enter into a new call of run next, and the state will contain the instruction pointer we already visited. So before we do the command, we have to check for, have we been here before? And we can do what we're trying to do here. Just, okay, where we are right now, add that to the set of visits. Sure, that will work, I think. The formatting is not great, but let's go. So we keep track of the instruction pointer we visit, we increment by an offset for jump, we do nothing except go 1 forward knob, and we change the accumulator with ACK. Yeah, only thing we need to do is halt when we detect an actual loop. Let's do that as first thing in this run thing. So if instructions dot state dot instruction pointer so if the current instruction pointer is in the set of visited, then we have loop. Then we have a loop, so let's just return the, not the state, we need to be able to detect that we're done. Maybe we should just make this function recursive. No, that would be bad, that would be really bad. Actually, we can do this halting thing outside of this function, more in this program, I'm thinking. So this is nice and clean, except for the keeping track of visited instruction pointers. That's not something assembly interpreter typically does, but okay. So let's do this check here. If we already visited the current instruction, then just return. Let's just return the state. We'll figure it out from there. And otherwise, we keep going. And that's not unit, that's state. I don't know why my mouse pointer keeps doing the hand thing. Okay, there we go. Let's run it. load everything in the REPL and run and pray. Okay, that was actually pretty fast. Before we check the result, I'm interested in how many instructions our program ran. Let's see, how many instructions did we run? Only 200. Okay, cool. Let's see if our program runs correctly. Yeah, we did. Continue to part 2. Just gonna copy paste the code. Now we can hack away. There's exactly one instruction corrupted. Now it gets interesting. So somewhere in the program there's either a corrupt jump that's supposed to be a knob, or a knob that's supposed to be a jump. That's a cool part too. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. So our instruction pointer has to leave the instruction set. That's when we have an end of program. And we just have to flip every jump or end every knob to the counterpart and see which of the program variants ends correctly. That's really cool. Jump plus 0 is a bad idea. Yep. Let's have code fix the program by just brute forcing our way through, but then we need to be able to detect end of program, and actually F# will crash if we try to dig into the instruction set with an instruction pointer. I'm thinking how we detect the end of the program in our current implementation. So if we detect a loop, we stop. Let's also stop if our instruction pointer falls out. So if our instruction pointer falls out of the instruction set. Oh, come on. Then we also halt. Oh, wait a second. So instructions, if it's a list of 3, then it has to be 0, 1. It has to be 3, so it has to be bigger or equal to the length of the instruction set. So that's our normal terminated condition. That's the infinite loop terminated condition. I think our program will halt correctly now. Now we just need to figure out which program variant halts. Yeah, and there's a difference, because now we just return the state. Also, if we infinitely loop, there's no way we can make the distinction between we detected an infinite cycle or we halted correctly. How are we going to make that obvious? Let's just use an option. So if we detect an infinite loop, if we detect an infinite loop, we just give up. We say, sorry, there's nothing we can do. And if we end validly, we halt. Okay, let's create all the program variants. It's also an interesting sub-problem. So what do we have to do? Basically, whenever we hit a jump or a knob, we flip that. So if we what's the easiest way? Just should we look at this like a parallel universe kind of thing? So recursively go down the list of instructions, and every time we hit a jump or a knob, we split into two parallel universes. One in the jump world and the other in the knob world, and then calculate all the variants recursively. It sounds like a weird analogy, weird enough to go ahead with it actually. Let's use pattern matching again. So if our instruction set is empty, we only have the empty program to return. If we have an ACK, we have let's first then calculate every variant for the tail. Yeah, let's calculate every variant for the tail, and that's a list of programs or a list of instructions. So then we have to let's call that A's. Let's call it something else. Yeah. So let's first calculate the variants for the rest of the program, and then for every variant program, let's append list punt let's append the original. Is this correct syntax? It's correct syntax, but I don't think the order is lining up. What's it called? List.concat? Does that concat a sequence of lists? That's not what we need. Append, that appends two lists. That's also not what we need, but we can make it work. Yeah, okay, so what are we doing here? If we have the empty program, we just have the empty program as a single variant. If we encounter accumulator, calculate program variants for the remainder of the program and just paste the append the ACK up front. And the interesting part is what comes now. So for example, let's do jump. For jump, we also need the recursive variance, and that's when the universe bifurcates, or when the universe splits into two, because we have all the variants of the remainder of the program, and we can now generate two variants. So one in the original universe, let's say, with just a jump. So that's a list of programs, and we have to duplicate. Yeah, so we have to duplicate. So actually we have to do the same as we did here. So rest, and we paste on the original instruction, and yeah, and flipping it to a knob. So calculate the remainder variants and then generate two sets of programs, one with the original jump and one with the knob. Probably should be testing this because I'm feeling it like quite uncomfortable right now. I don't generate parallel universes on a daily basis, is what I'm saying. I don't know why I keep the A, the J, and the N. But anyway, so this is keep the original one, and this is jump to the flipped one. In theory, this is a variant generating function. That's not something we have in the exercise or in the example. No, we're just flipping as we go. Let's try to run it, and if things blow up, the problem will probably be in variance. So let's try troubleshooting then. It's not lazy, no, I'm using lists, so this will actually generate a whole lot of instruction sets, a whole lot of programs, I'm thinking. Let's see if this ends. Sorry, we need... Are we doing something? No, we're in an infinite loop. Stop. We're in an infinite loop because I'm generating a whole lot of programs. And maybe even too much. So how will we do this in a smarter way that does not burn our computer? We could just make this lazy. So it only calculates the next variant when we need it and not up front. That's one way of doing it, I think. Would that be hard to do? The input program is always a list, that's not a problem. So whatever we return has to be a sequence. So maybe if we just port everything to sequences. This is actually going to do something, I'm not sure. I think we might need to use the yield keyword. What's it not liking? Oh yeah. Oh god. I don't know if let's go through with it just to see if hypothetically speaking this would work. But it's a pretty invasive micro refactoring for something I'm not even sure it's going to work. I went down a dark path today. So this is the same thing, except it's using... Oh, it's not the same thing. What's still not okay? A list does not match the type of sequence. Sorry? Sorry, what is it saying? Sequence of lists. Oh yeah. Yeah, this also has to be a sequence. Not sure where we're going with this. Yeah, okay. Almost there. Jesus. There we go. Let's get rid of this quickly if it doesn't turn out to be evaluating our lists. I'm not really thinking, I'm just trying. It's not a good approach to problem solving in general. So what did we do just now? We replaced basically every occurrence of it being a list to just moving to singleton, and somehow I'm hoping that this will make our variant generator lazy. What is it actually doing? It's pattern matching on the list. Segment, yeah, it might actually. Let's see. Looks good actually. We just generated our variants, but we generated them lazily. And if we now do all variants, give me the first program. Yeah, looks correct. So forget I was skeptical, and let's forge ahead. Now we have all the possible variants of the program that could return. Now let's run them all until we hit the first one that ends, and ending we indicate by returning a sum. So we're using option to halt. So all variants, what's it called? Choose filters the sums, yeah. We do run program instruction state. So it's run program with the variant. Let's do it like this. So run our program with the variant and initial state. Actually, this can be a list, not a sequence. The program itself can be a list. It's just the generating of the variants that should have been lazy. Let's clean that up later. Let's first have our solution. What's the Kent Beck quote? Make it work, make it right, make it fast, something like that. But making it fast was pretty important right now because generating a metric ton of variants was not that impressively fast. What are we doing right now? We're saying lazily generate all the variant programs that could halt and then keep running until we hit one that halts as it should be, so not with an infinite loop. And that's because we use sec choose and the option thing. If you use those two in combination, we're now filtering out all the programs that do halt, but we only need a single one, or the first one. There's probably only one, but let's just take the first halting program. And that should be our part 2 end state. Let's go. Ta-da! And it gives us an accumulator. Which is not correct. So, which part I was not sure about? The generating of variants, maybe. The running the program after the instruction pointer could also actually be a bug. And there might even be a bug in this thing that we have not yet seen. That would be surprising because we've solved part 1, maybe by accident, who knows. Let's dig into problem solving mode. I'm gonna put on my debugger Santa Claus hat. This is my punishment for going too fast and not testing my code. So let's go. Let's use the example to figure our way out of this. Yeah, let's use this one. I'm just gonna create a new text file, drop the example in there. Okay, part 2 is where we are at. Let's parse the example. Instructions is where we do the parsing, and we use it here. So let's do the same for the example. Let's call this parse program. There we go. So this is our parser. This is the variant generation. Yeah, okay, that's good enough. So let's parse the example. So that's interesting. My IDE knows what's coming, so it can invert types. My REPL cannot. So if I run enough code in the REPL, it'll figure it out. There we go. Nop0 ac1. Let's put them side by side. Nop0 ac1. Jump 4 ac3. Jump -3 ac -99 ac1. Jump -4 ac6. So parsing looks correct. Parsing looks correct. Let's see the variant generation in action. Yeah, let's look at the first generated program. I shouldn't have made the programs themselves lazy. That makes no sense. Okay, so first variant of the program. Is that the original program? Nop ac jump. Let's print out two side by side. Nop ac jump ac jump ac ac jump ac. So yeah, there we flipped a jump to a nop. Actually, it should be, we should be able to iterate all the variants for this really small program, right? So we have 1, 2, 3, 4 flips. So what is it? 2 to the 4th, 2, 4, 16-ish. Should we have 16? Yeah, we have 16 variants. That all sounds correct. Where is the problem? Where is the problem at? Well, we have an accumulator, yeah, we have jump, yeah. We do have to give the accumulator value, right? Yes, we do. Oh no. Oh no. I went a bit too hardcore. We have to change only one jump to a nop, not all possible combinations. So I made the problem a bit harder than it actually was. Did I? I probably did. But yeah, I probably did. Let's run part 2 for the example. Then we have something smaller to work with. Oh no, it's correct for the small example, but not for our bigger one. I hate it when that happens. Let's wrap everything in a function, and then we can write a test. Steam, what are you doing? Or whatever. Let's just extract the instruction pointer. There we go. Accumulator, sorry. Let's hardcode this in a test so we can start to noodle around a bit. No, doesn't like it. Maybe this is better. Yes, that's better. So we have our regression test in place. Let's actually inline everything. Oh, come on. There we go. So this is actually our run the program. Get with the program. So I just figured out that we only need to flip one jump to a knob. Let's get rid of this. One jump to a knob or one knob to a jump, and not all possible flips. That sounds like an easier problem, so why am I having a hard time wrapping my head around it? So if we calculate all the variants, the return type is still the same. It's a sequence of programs. Is the problem? The problem is here. We either flip jump and keep the original program, or we keep jump and flip one of the recursives. Yeah, so we keep jump and flip the original program. Yeah, okay. Whew. So we keep jump and flip, that's the first part, yeah. Or we flip jump and do not flip the rest of the program, we just keep the originals. Really making a mess right now by flipping between sequences and lists. Okay. What's the difference with prog? That's instruction list, and rest is, oh yeah, it's a list of a list. Oh yeah, we don't even need to. Okay, step back. Let's try this again. So we either keep jump. This is this thing. This thing is saying keep jump. But then we need to flip something else in the program. So this is what rest is saying. And rest can be several different programs because every flip results in a new program. So it's actually seg-append, what we're doing below. And this doesn't work because it's not one, but multiple programs, right? So we need to do recursive append. Yeah, so we generate the alternatives, we paste the original jump on it. This is way too complicated than it should be with all the secking and the mapping, but I'll figure it out after we get it working. This is part 1, where we keep the jump but flip everything else. And the other part is where we flip the jump and keep the program as is. So flipping the jump is easy, and keeping the program is actually it's saying it's a single program we're returning, and it's actually jump J and proc, but then it's a sequence, not list. Yeah. So this is a list. Let's make it a sequence. So this is again a program, so a single list, and if we make that a singleton, that works. So these are the two parts. This one is the easiest one. So let's put this up front, and let's just do let's keep both of these. So this is the normal case, no, the recursive case, and this is the, no, sorry, this is the recursive case. No, this, I'm getting really confused. This is the recursive case. Yeah, this is what I'm actually trying to do here. This is the non-flipped. This is the flipped. There we go. And append non-flipped and flipped. This is kind of where I want to go, but I'm reading it and it's not correct. So non-flipped is saying generate all variants recursively and then just paste jump on it, the original instruction, and otherwise flip the instruction and keep the original program because we already did the flip. And this sounds better or easier than the original part. And here it's a NOP, so it has to be a NOP here, and we flip here. Let's go in my head again. So accumulator, nothing needs to happen, and the nothing needs to happen is way too verbose, so that's a smell here, but we already know this can be cleaned up. If we meet a jump, generate all the other programs containing one flip potentially, and just paste jump in front because we haven't flipped it, yeah, or flip jump itself and keep the remainder of the program intact. And those are the two alternative universes, and they're both valid. Yeah, sounds better. So variant generation is now different. We still have 8. Let's see if we still have a different value for the accumulator. I don't remember what I inputted before, but it's different. Okay, there we go. It was I made the problem harder than it actually was. That was that was my main problem. So kids, read the day's exercise carefully. That's like the moral of today. This solves day 8. What I'm going to do is clean this mess up, because this has become an unholy garble of sequence operators and it's not necessary. But I won't bore you with this refactoring any more than I did already. I'll just show you tomorrow morning. Thank you for watching and see you next time. Bye.